In this video, we discuss implicit differentiation, which allows us to compute dy dx given a relation involving x and y. So here's a relation involving x and y. It's relatively easy to solve for x as a function of y. We can just move these terms to the other side and then take the square root. We have plus and minus the square root of a particular expression. But it's difficult in this case to find y as a function of x. Since it's difficult to find y as a function of x, we might compute the derivative using what's called implicit differentiation. It's actually relatively easy. We're just going to differentiate both sides with respect to x. And we do this assuming that y is a function of x. So when we take the derivative of this, we take the derivative term by term. The derivative of x squared can be found using the power rule. So you bring the power down, multiply by x to the 1 less power. Oops, I accidentally wrote a 3 there instead of a 2. The derivative of this constant times y cubed can be computed using the chain rule. You just have to remember that y is a function of x. So you think of y as the inside function, which we don't know, and we want the derivative -2 times that inside function cubed. Well, -2 times some function cubed has the derivative of -2 times 3 times the original function squared. And the original function in this case is y of x. And then we multiply by the derivative of the inside by the chain rule. We call that implicit differentiation. Sometimes people will say, if you see a term involving a variable that is different from this variable here, you just differentiate with respect to that variable, which gives us the -6y squared, and then you multiply by a y prime, or you multiply by a dy dx. But the reason that works, the reason why that's true, is because y is a function of x, and you're really just applying the chain rule. So you take the derivative of the outside, evaluate the inside, multiply by the derivative of the inside, and then we're going to add 4 times the derivative of y with respect to x, which is just dy dx. Or if you prefer, you can write y prime. Either one is fine. And then we get a 0 on the right-hand side. So now we're trying to get dy dx by itself. We've got 2 terms involving dy dx and this one term that does not involve dy dx. So we're going to subtract that from both sides. So we'll have a -2 on the right-hand side. And then on this side, we see that both of these terms have a dy dx in them. So we'll factor out the dy dx. So we'll have dy dx times -6y squared times dy dx is our first term. And then dy dx times a +4 is our second term. So now we have dy dx times this equals this. To get dy dx by itself, we just divide both sides by the coefficient there. And if we want to, we can take that negative from the numerator and multiply by that negative in the denominator. We could just move it. So we've got a 2x in the numerator. And then we'll take that negative times the -6y squared makes that +6y squared. And the negative times that 4 gives me a -4. So this gives me the slope at any xy that is on the graph of the function. So you have to be very careful about that. I think I said any point on the function. What I meant was any point on the graph of the relation. One thing I want you to notice is that this expression involves both x and y. So we need to find both x and y. Typically, what I do in a case like this is if I don't have a graphing calculator, I would just select an x value or a y value and then solve for the other one, and that would give me a point on the curve. For example, if y is equal to 1, we have x squared minus 2 times 1 cubed plus 4 times 1 equals 2. So we just end up with x squared plus 2 equals 2. So x squared equals 0. So that means x equals 0. So that means the point x equals 0, y equals 1 is on the curve. Now, if I want to, I can substitute that value into here. And so I end up with a slope of 0. I think I must have made a mistake somewhere. I'm not sure what I did wrong. Maybe I wrote down the equation incorrectly. But let's look at the graph of this relation and see sort of what we see on the graph. I feel like the point 0, 1 is not on the graph because I've looked at this problem before. Okay, so this is the graph of our function, or excuse me, our relation. It's kind of cool. It has 2 pieces. Got this piece, which actually does have the point x equals 0, y equals 1 on it. The tangent line, I would assume, has a slope of 0, which is consistent with the calculations that we did on paper. But there are 2 other functions here. Basically, I'm just looking for a part of the graph where the y values or the x values don't repeat. So we have 3 pieces, there's 2 pieces, but 3 functions. We've got one function where the y values go from 1 to infinity, or 1 to infinity. So that's this right here. Just that top part. And then where we had the other y values. Now, if we look at the graph, I was able to look at the graph before. And it was labeling the points before, but now it's not labeling them. Desmos is acting a little funny right now. But there's a y value right here, an xy pair right here and here. So we've got a function on this sort of top piece of this closed curve, and then there's a function on this bottom piece of the closed curve. Now, Desmos.com was immediately giving me sort of the points of interest. So it was giving me this location, and this location, this location, and this location, and this location. So sort of the extreme values, the farthest to the left and the farthest to the right, the y-intercepts, and then it was giving me the x-intercepts. But it's not doing that anymore. So I'm just gonna have to rely on the work that I did earlier. So before, when I looked at this, I saw that my y values from negative 0.816 to the y value of 0.618. That is one function. So if I graph that for you, it's just that orange part of the curve. And then this y value turns out to be negative 1.618. And so we have that as our curve. Now, I think it would be relatively easy to figure out all of these y values. We got 1, 2, 3 y values. So we know that when x equals 0, we have this cubic equation for y, and we would be able to solve that cubic equation just by using possible rational roots and things like that. And we'd be able to find those points of intersection. Similarly, if we let y equals 0, we can find the points of intersection on the x-axis. We know x equals plus or minus the square root of 2, so that's this point here and this point here. But these values where the tangent line would be vertical would be more difficult to find. But we could actually find those using our definition of the derivative, or the derivative that we found, that derivative formula that we found using implicit differentiation. So I've got this formula, and I just typed this in. After doing the calculations by hand, we had y prime as 2x divided by 6y squared minus 4. Now, if I set that denominator equal to 0 and solve for y, then I will know which y values can give me a 0 in the denominator here. And actually, I don't remember what those are off the top of my head, but we would just have y squared equals 2 divided by 3. So y equals plus or minus the square root of 2/3. And so those would be our values here and here. That doesn't sound right. I would think that that would be it. Let me see. Actually, let's do that calculation on paper and see if it works out. So that doesn't actually do much for me. The square root of 2/3 is some number between -1, or a square root of 2/3 is between 0 and 1. And I know that these y values are these, well, the y value is square root of 2/3. Do. I see what I did wrong. The y value here would be square root of 2/3, plus or minus square root of 2/3, and then the corresponding x value could be found by substituting those y values into the original equation. So we could do all of that, all of those calculations by hand, and that would be fine. But yeah, so this, I don't actually know what that value is. Oops. About 0.816, which is consistent with this value. Y goes from negative 1.6 or 1.618 to negative 0.816. So yeah, that makes sense. But yeah, we can substitute these y values, y equals the negative of that, into the original function. And then you can solve for the corresponding x value. And that's actually relatively easy to do because you just end up with x squared equals a number and you can take the square root of it. But the idea is we're able to identify these 3 functions. And on each of these 3 functions, the slope is well defined, except for at these points here and here, which is why they're the boundaries of our 2 functions, this function, this function, and this function. But then on each curve, we can draw a tangent line. On the first curve, I chose y equals 1 and x turned out to be 0. That means the tangent line is just going to have an equation y equals 1. So let's sketch y equals 1. It's a horizontal line, nothing fancy, not that impressive. But that was the calculation that we did on paper. There are also more interesting y values. I think I saw this point and I thought it was y equals 2 when x equals 3, and that was inaccurate. When I tried y equals 2, x equals 3 right here, or x equals 3, y equals 2, but you see when you look at the graph, if you look at it very closely, there's a little bit of a gap there. So y is actually equal to 2 when the x value is a little bit greater than 3. If you substitute y equals 2 into the equation, you get x equals plus or minus the square root of 10, which gives us these 2 points. And then we can substitute these values into our formula for the derivative. Actually, let's bring that with us. This is what we calculated on paper. And at those values, our slope turns out to be a square root of 10 divided by 10 in one case, and negative square root of 10 divided by 10 in the other case, depending on whether x is square root of 10 or negative square root of 10, because we have that x factor in the numerator. When x equals a positive square root of 10, that means we're over here. We've got this as our tangent line. And we're using y equals the y value there, which is 2, plus the slope, which is calculated by hand, square root of 10 divided by 10, times the quantity x minus x naught, where x is the square root of 10. And if you zoom in, you can see that that tangent line has the same slope as the curve itself. And the same is true at the other side. You just got a different slope. It's negative square root of 10 over 10, and then we're subtracting a negative square root of 10. So that means we add square root of 10 in our formula. And so we get that line. And that's also tangent to the curve. So we can see that this formula for the slope that we calculated using implicit differentiation is actually giving us the right value. And then if you want to find points on this curve, I just chose a convenient x or y value. I said, well, I know that x is equal to, or y is equal to 0 here at these points. And I solved for x. So I got x equals plus or minus the square root of 2. Those are those points of intersection right there. And then I said, okay, let's plug these values into our derivative formula that we found using implicit differentiation by hand. After you simplify, you're gonna have y equals the initial y value, which is 0, plus the slope times x minus the square root of 2. After we simplify, we get this. And then you have y equals this original y value, which is 0, times the slope, which is square root of 2 over 2, times x minus a negative square root of 2. End up doing all the calculations by hand, and you get this. But you can see if you zoom in that it's giving us the right slope. Now, if you're saying, oh, I want to see those calculations, we can do them. Let's do them real quick on paper. In each case, you substitute those into the formula for the slope. We're going to evaluate our slope at square root of 2, 0. So in our numerator, we get 2 times our x value, which is square root of 2, over 6 times y squared minus 4. So you end up with a negative square root of 2 divided by 2 as the slope at this location. So y is equal to the original y value plus the slope, which is the change in x divided by the change in y, times the change in x. So change in x over change in y times change in x gives us change in y. And change in y plus the original y value gives us the new y value. The original y value was 0. The slope is negative square root of 2 over 2. And then we're subtracting square root of 2 there. So if we distribute, negative times a negative is a positive. Get square root of 2 times square root of 2 is 2. 2 divided by 2 is 1. And so that's how we get that equation. And then at x equals negative square root of 2, we just get a negative in the numerator. And then we'll have this negative value divided by that negative value gives us a positive slope. That makes this positive. And then we'll be subtracting a negative square root of 2, which gives us this right here. So if we distribute, we'll have a positive slope. And then that times that will give us a positive 1 again. So that's how I came up with those formulas. It's very simple, very easy to understand. So let's look back at our graph now on Desmos. Let me do that. And then to find points on the purple graph, I looked for a y value that was in the range for the purple graph. I saw a negative 1.5 was there, so I just substituted y equals negative 1.5 into the equation of the original curve. It's all the way up here. So the graph looks like that. But we're just interested in this branch down here. And I said, okay, let's substitute y equals negative 1.5 here and here. So we did the computation, moved those constants to the other side, took the square root, and we got x equals plus or minus the square root of 5 divided by 2. And so that gave us these 2 locations, those 2 points on our curve. And we said, okay, well, how do I find the slope? Well, I substitute into that slope formula again. Super easy. That's our slope formula. So you're going to substitute that in for x, substitute that in for y. You got some fractions and some sort of arithmetic that you have to do, a little bit of computation. And then, but after you simplify, and it turns out that you're going to get 2 times the square root of 5 divided by 19 as your slope. And then at x equals square root of 5 divided by 2, we get the y value on the tangent line is the original y value plus the slope times x minus the x value, which is the square root of 5 divided by 2. That gives us that line. If we simplify that, we get this. And then at the other x value, you get, see, that's the same. I wanted you to see if that's the same line. And then over here, you have the same slope almost, except you've got a negative in front because you've got the 2x in the numerator, which is the only difference between this expression evaluated at this ordered pair and this expression evaluated at this ordered pair is the negative sign that comes from the x value. So we've got this slope, which is negative, and then because of the sign change, when you substitute in the negative value for x, when you simplify, you get the same y-intercept. So you get that. And we still have these points up here, so I should probably get rid of those. It's from the other example. But you can see that those tangent lines are tangent to the curve at each of those locations. So I might be interested in finding where the relation has horizontal tangent lines. Because the points where the relation actually has horizontal tangent lines are those points where our graph goes from one function to another. We have a well-defined slope dy dx, as long as that denominator is non-zero for that expression involving dy dx. So those vertical tangent lines tell us, well, that's when we're going to go from this piece to that piece. Then to find that, well, what do? We just set the denominator equal to 0 for the original expression. So let's do that on paper. So notice that those vertical tangent lines occur at a y value that is negative. Okay. Now we'll look at the computation on paper. So here's my equation for the slope. I set the denominator equal to 0. And I add 4 to both sides, divide by 6, take the square root of both sides, and I get actually 2 y values where that denominator is 0. At the negative y value, we know that we have those vertical tangent lines, at least from our graph. So we'll substitute those negative y values here. I was doing this before and I realized that I chose the positive y value and that's not going to work. But this is the corresponding x value. I'm going to use desmos.com to get those x values and to estimate this one as well. So let's do that. Okay, so we know that that's true. I actually want to graph y equals the square root of 2/3. That y value, y equals the square root of 2/3, is not even in the range of our function. We actually skip that y value. When we go from this y value to that y value, we miss all the y values between whatever this y value is at the very top there. A little bit difficult to see, and y equals 1. It looks like 0 and 0.816 and 1. So we miss all of those y values in between. But our, oh, actually, no, that's the y value. That's a numerical approximation of the square root of 2/3, sorry. I'm having trouble figuring out what that y value is, although we could do it if we wanted to. It's just sort of beside the point when we're talking about implicit differentiation. But if I want to find the x value that corresponds to that vertical tangent line here and here, I just substitute this y value, the negative y value, which is where this bottom function switches into this top function, sort of the point of intersection between those two functions. We'll just substitute this into our equation for x and then solve. The equation just had an x squared in it, so it'd be easy to solve for x as a function of y. Our x value is going to equal the plus or minus the square root of 2 plus 2 times that y cubed. So I'm just typing in the answer, -4 times y to the first. So that's our x value approximately. So we've got, this is our x value and that is our y value. And of course, we could simplify it. We plot that as an xy pair. I'm just choosing not to simplify. We could, we just don't want to take the time in class today. So we've got that. And then the other x value is the same, but with opposite sign because it was a square root. We get a plus or minus of the same, with the same magnitude. There's the other point. And so those are our points of intersection. And if we let x equal that value, we have the vertical tangent line there. And if we let x equal the opposite of that value, we get the other vertical tangent line. Those vertical tangent lines are giving us the locations where we switch from a top function to a bottom function if that curve happens to be a closed curve. In that case, it's really helpful to have a graphing calculator that can show you sort of what the relation looks like. And I know that these look really bad, but we could have simplified them. We just chose not to due to time constraints. All right. So this is about implicit differentiation. Now, let's look at a couple of those points. I like that those points, that the points of intersection with the x-axis a lot. The slopes were plus and minus square root of 2 over 2 at that location. You might be interested in finding the second derivative at that location as well. You might say, well, what does that mean? Well, the second derivative tells us how the slope itself is changing at a location. Now, if we look at the graph, we can see that if I draw a tangent line right here, it's vertical. And then if I draw tangent lines on this curve, all of them are going to have positive slope until we get up here to the very top. Then we're going to have a tangent line with a slope of 0. So we go from a derivative that is essentially infinite, it's undefined because the slope, we're talking about a vertical tangent line where the limit definition of the derivative would give us infinity or negative infinity. And then we let those slopes change as we go from here to here, and eventually the slopes are 0, but they're all positive on this side. And say, okay, well, they're all positive. Well, that means the derivative is positive. But think about how that slope is changing. It goes from infinity to something that's very steep but less than infinity, and then less steep, and then less steep, and then less steep, and goes to 0. Well, the slopes are decreasing. So they're going from something very large to 0. So they're going from a very large value that's positive all the way to a 0 value. So I would expect the second derivative, which is telling me about the rate of change of that slope, to be negative because the slopes themselves are decreasing. And then we have something similar on the other side, where I'd have a 0 slope, then a negative slope, which isn't very large in magnitude, and then a steeper negative slope and a steeper negative slope, and eventually we get a slope which is essentially negative infinity. So the slopes are getting larger and larger in magnitude, but more and more negative. So that second derivative, which tells us the rate of change of the slope or the rate of change of the derivative, is decreasing. So it goes from infinity through a bunch of positive values to 0, and then it goes from 0 to a negative value into increasingly negative values back to negative infinity. So that's what I would expect on this curve. So I'm expecting a negative slope here, or excuse me, a negative second derivative on this curve. And you'd say, how do you find the second derivative? Well, you just take the derivative of the first derivative. It's actually relatively simple to do. So we're going to do that on paper. Okay, one thing I just noticed was that the numerator and denominator have a common factor of 2. So I'm going to factor 2 out of the denominator. 2 times 3y squared gives me the 6y squared, and 2 times -2 gives me that -4. The 2's reduce. And our slope turns out to be x divided by 3y squared minus 2. Can't believe I didn't catch that earlier. Now, if we're taking the second derivative, that's just the derivative with respect to x of the first derivative. We'll have the derivative with respect to x of this quotient. We can find that derivative using implicit differentiation as well. If we call this the high function, of course, it's high, and this is a low function. Sometimes I abbreviate that HI and I abbreviate that one LO. The mnemonic for the derivative of a quotient is low D high minus high D low over low low. And the differentiation operator applies to whatever's in front of it. So we're going to have low D high, and that's with respect to x. And I'm just going to write the derivative of x for right now, and then we'll do that calculation in another line. Minus high D low, and remember that's differentiation with respect to x again. All divided by low low. And the derivative of x with respect to x is just 1. And the derivative of 3y squared with respect to x requires the chain rule because y is a function of x. So we say, well, what's the derivative of 3 times a function squared with respect to x? It'll be 3 times 2, which is 6, times that function raised to the first power. Then you put the inside function back inside. Don't do anything to it, just put a y in there, and then multiply by the derivative of y with respect to x, or you can call that y prime. And then you subtract the derivative of 2 with respect to x, which is just 0. And then we've got this, that 3y squared minus 2 quantity squared in the denominator. So we end up with this minus 6xy times dy dx, all divided by this. Now, whenever we're using implicit differentiation, we do expect an expression involving x and y, but we don't expect an expression involving the derivative. This dy dx, we need to substitute, but we can substitute it. We already know what it is in terms of x and y. Dy dx was 2x divided by this, or simplified, it's x divided by this quantity. So we can replace this dy dx with that expression. And then if you want, you can simplify. And I would prefer to simplify because I've got that fraction within a fraction. So I'm going to take this numerator and multiply by the denominator of the smaller fractions. That's this 3y squared minus 2. I'm thinking of this as one term, and then this is one term because we're multiplying all these together and we're subtracting this expression from this expression. So I'll take this times this, and then I'll subtract this times this expression here. And that's legal as long as we do the same thing in the denominator. So here, this times this is going to give us that 3y squared minus 2 quantity squared. And then when I multiply this by this, the denominator is clear, and I end up with 6xy times an x is a 6x squared times y. Multiplied by this expression cubed. So I've got 2 of them there, and then I'm multiplying by an extra one. And that is a formula for the slope at a particular location. Now at those x-intercepts, which were given by x equals plus or minus the square root of 2, y equals 0, we can substitute those in here and find out what our slope ought to be, or excuse me, our second derivative ought to be. Y equals 0. Well, actually, if y equals 0, we get rid of all the x's altogether because this x, the only term involving x is multiplied by a y. So we get a 0 there. And then this is just going to be a -2 squared, which is 4, over -2 cubed, which is -8. So we get -1/2 for our second derivative. Since that value is negative, that just tells us that the slope is decreasing, which just means that the graph kind of looks like this. When the second derivative is negative, the graph is what we call concave down or concave downward. And that means it looks like this sort of up facing down as opposed to facing up. And the way you can think about that is that the slope is 0 at the top, the slope is positive over here, and the slope is negative here. And so it goes from very, very positive, very steep positive slope, and then the slopes decrease and decrease and decrease until you get to a slope of 0. And then as you go from here to here, the slopes start with sort of -1/2, and then -2, and then -10, and then so they get increasingly negative, and they get more and more steep as you go farther to the right. And so since we're going from positive to 0 to negative, this is what we call concave down or concave downward. And I'm actually not sure if you're supposed to put that downward or down. I don't know. I'm not an English major. But that second derivative being concave down is consistent with the graph that we see on Desmos.com. So our first derivative is positive square root of 2 over 2 over here and negative square root of 2 over 2 here. And then on that orange curve the whole time, the slope is, or the second derivative is negative. When we evaluated the second derivative at these 2 points, we got a -1/2 in either case. The graph is sort of concave downward. This part is concave upward. This top branch, it's a little bit harder to see when the second derivative changes signs from concave downward to concave upward, because it kind of looks like it's concave up here, and then it sort of flattens out and it doesn't look like it has any curvature at all. So that's actually kind of interesting. But it is a little bit unrelated to our discussions of implicit differentiation. So let's move on. That's the first example. I think we've done enough with that first example for right now. And we've looked at the first and second derivative and how to find points on the curve. But we will come back in a different video and look at a second example.